So hello everyone and welcome back. I'm gonna ask everyone who can please open their cameras so we get a more interactive talk, and makes a big difference for the speakers as well as for everyone. And I'm very happy today to host Steve Fleming. Steve Fleming did his PhD at UCL with Chris Frith and who else? And Ray Dolan, right?
Yeah, that's right.
Yeah. And then did a postdoctoral fellowship with Nathaniel Daw, and then another one with Matthew Rusford. And he has won numerous awards, including the William James Prize from the ASSC. And he's a rising star of the APS, and has received a BPS Spearman Medal. And despite his very daunting CV, he's a really, really nice guy. And he now has a lab where he's a principal investigator at UCL, and welcome. And he leads a group working. He's very famous for his work on metacognition and consciousness and decision making. And we got to know each other well working together at the Association for the Scientific Study of Consciousness, the ASSC. And I'm very happy you had the time to come talk to us today, Steve. Very excited to hear about your work.
Great, cool. Well, thank you so much, Roy, for the invitation. And I guess it is one silver lining of the current situation that we are at least able to have these talks over Zoom. But I just also want to mention that I was really sorry not to be able to get out to Israel earlier in the year for the ASSC conference that Roy was organising. So I've still never been out to Israel. And so I'm hoping that when all this is over, I will get the chance to visit you all in person. So what I'm going to do today is to talk about a recent line of work we've been pursuing on metacognition and changes of mind. And if anyone wants to interrupt with questions as we go, then that's fine by me. Feel free to do so. Okay, so just a brief introduction to what we're doing in our lab. So as Roy mentioned, we're focusing on understanding metacognition, so how we reflect on and evaluate other cognitive processes such as perception, action, and memory. We're interested in the computational and cognitive and neural bases of metacognition. And so that's kind of one line of, we have one line of, I guess, more basic science work, understanding metacognition in and of itself, but we're also interested in how metacognition might help us understand several other things, such as the functions of the prefrontal cortex, the role of metacognition in consciousness, in mental health, in the control of decision making, and also how we interface with technology, such as knowing when we might need to write a list or offload to artificially intelligent assistants. But for the purposes of today's talk, I'm going to focus on this link here. So how metacognition might play a role in the control of decision making, and in particular, how confidence might affect how we, whether and how we change our minds. So to begin creating, to begin studying changes of mind, we need some kind of definition of what we're seeking to study. So this is one useful definition we've been working with in the lab. So change of mind is a reversal or re-evaluation of a previously held decision or belief, either due to endogenous post-decisional processing and or the receipt of new evidence. So to give you a concrete example, you might collect some information together about two political parties and listening to the news and so on, and that might inform your decision about who to vote for in the election. But then after you voted, you might get some new information coming in. You might reflect on whether that was a good or a bad idea, and that could potentially lead to a re-evaluation or a reversal of that previous choice. And this is obviously quite complex and potentially long process in the case of voting for a political party, but we can also think of changes of mind and post-decisional processing as occurring very quickly. So this is a nice example, is the undo button in Gmail that Google installed in 2015 in response to user requests. So presumably there were lots of people emailing Google to say, I really want to undo an angry email that I've just sent. Can you put a button in place that allows me to do this? And as long as you hit this button up to 30 seconds after you send the email, then you can undo that being sent. So the idea is that we have this kind of continued processing of information, either endogenously or exogenously, after we make a decision. And we started thinking about what might the role of metacognition be in promoting these kind of changes of mind. And so the connection here is the idea that in a core variable of interest for metacognition is the ability to represent how confident we are about different cognitive processes, such as how confident we are in our memories or our perceptions. And so this led us to start thinking about how does confidence in our beliefs and decisions affect how we process new evidence and whether we go on to change our minds. So in today's talk, I want to try and touch on the following 4 questions. So first of all, how does confidence modulate whether or not we change our minds? And then look at the role of confidence in more active seeking of information rather than just passively processing information that's coming in. I'll then try and expand out a bit and talk about how these metacognitive features of decision making that we can measure in the lab might also predict real-world political attitudes. And finally, I want to end on a more optimistic note and to point the way forward to how we might be able to harness metacognition in terms of metacognitive training, boosting people's self-reflective capacity to then improve their open-mindedness to new information. Okay, so let's dive in. So here we're not in the lab, we're studying change of mind, not about political decisions, but about something much more basic. But I don't think are these videos going? Yeah, they are. So what we're using here is perceptual decision making as a model system, often using these random dot motion stimuli where we can precisely alter the amount of evidence that's available for one or other choice. So subjects are asked to decide whether the dots are going to the left or to the right. And this allows us to create graded changes in the difficulty of the decision by changing the coherence of the random dot motion and strip away any higher level cognitive or emotional content from these decisions. And the nice thing about using these kind of stimuli is that we know quite a lot from work in monkeys and humans about how these decisions get made. So in particular, circuits in the prefrontal and parietal cortex are thought to accumulate motion evidence up to a threshold level, at which point a decision is made. But we know quite a lot less about how, after a choice is made, how post-decisional evidence then affects whether or not the subject goes on to change their mind. So we're going to kind of extend out the classical perceptual decision paradigm to add in new evidence that's coming in after the choice is made. And particularly, we're going to be interested in how does the confidence of the subject at the point of time where they make the decision, how does that modulate or affect the processing of new evidence? Now, there are already some strong hints in the literature that this post-decisional phase is not simply just a carbon copy of the pre-decisional phase that's just copied over and inserted after the action. So this is a recent study from Tobias Donner and Marius Usher's team. And what they did was ask subjects to make an initial binary decision about whether a patch of randomly moving dots was going clockwise or counterclockwise to a boundary. And then after that initial binary decision, they were asked to indicate the precise direction of motion. And this was also informed by a second presentation of the motion evidence. And what they could find is that there is selective processing of post-decision evidence that's in line with the initial choice. So this is a form of perceptual confirmation bias. If I say counterclockwise, then I'm going to be biased towards integrating more counterclockwise evidence when I see the stimulus again than if I said clockwise. And so this kind of paradigm led us to start thinking about what's the role of confidence in this initial decision in the incorporation of the post-decisional evidence, how that might shape whether we go on to change our minds about an initial choice we've made. So this is the paradigm that I'm going to talk about in we're going to use variants of this paradigm in a few different studies that I'll talk about today. So this was work that was led by my recently graduated PhD student, Max Rollwager, and Elisa Lucen, who was a master's student in the lab at the time. And the idea is very simple, similar to the Telluri setup. We have an initial patch of moving dots. Subjects make a binary decision together with a confidence rating, so they have to say whether they're going to the left or right. And then they get a new sample of post-decision evidence, after which they have to then make their final decision and confidence estimate. So a couple of important features about this design. So first of all, we titrate the coherence of the initial stimulus for every subject using a staircase procedure to target a medium level of accuracy, around 70%. And importantly, the post-decision evidence is always helpful. We're not trying to trick people here. We're always giving them the same direction of motion, both pre and post-decisionally. And the post-decision evidence could either be of the same coherence as the pre-decision evidence or of a coherence level that was a higher multiple of that pre-decision coherence level. So you either got the same strength of evidence or slightly higher strength of evidence when you saw the dots again. Okay, so what we can then do is think about, well, what should we see in this kind of paradigm when we look at people's final decisions and confidence estimates after seeing these two samples of evidence. And from a simple computational model that integrates the evidence and the choice we've made, then intuitively what should happen is when I'm correct about my initial decision, remember we're always giving people helpful samples of evidence here. So when I'm initially correct, then when I see a new sample of evidence, that will just go on to confirm my initial choice. And as a function of the strength of that new sample, I'll just go on to become more confident. Whereas if I'm initially incorrect about my decision, then as I see stronger and stronger post-decision evidence, that's going to disconfirm my initial choice, and I'll go on to be less confident about that choice, right? So you should see this kind of interaction pattern where when I'm right and I get new evidence, I become more confident. When I'm wrong and I get new evidence, I become less confident. And what that predicts is that also, so this, you can imagine just binarizing this space. When I've got high post-decision evidence strength, the difference between my confidence in being correct and wrong is biggest. So this predicts that I should just get more and more accurate as a function of the post-decision evidence strength. So that's kind of intuitive, right? And so that's exactly what we see in the data. So your final decision tends to be more accurate than your initial decision. So that's evidence that you are actually incorporating this post-decisional sample. And we also see evidence for this divergent pattern of confidence rating. So when I'm correct in green, I maintain a high level of confidence. If anything, it ticks up a bit towards the end. But importantly, when I'm wrong initially, then as I see stronger post-decision evidence, then that serves to disconfirm my initial choice, and I get less and less confident as a function of the strength of the new evidence.
Steve? So we can all do some evidence accumulation and change our confidence, whether this will come back immediately or whether Steve will have to disconnect and hook back on. Okay, yeah. Steve, you're still muted. Can you?
Sorry, I lost you guys?
Yeah.
Okay. Hopefully that's just a temporary glitch. See if we can get back to where we were. Right. Okay, are we back?
Yeah.
Okay, cool. Right, let's hope that doesn't happen again. The gods of Wi-Fi hopefully will continue smiling on us. Okay, so right, so what we're then interested in doing is looking at, so this is kind of like just the basic behavioral features, but we want to know, how does this initial decision and confidence estimate affect or modulate how we process the new evidence that's coming in?
Sorry, Stephen, I'm not sure if you explained the last graph over there of changes of mind, but if you did, we missed that one.
Okay, thank you. So yeah, so this is just another way of viewing this data, really. So this is saying that when I'm initially correct in green, I change my mind less often, which makes sense, that's adaptive. Whereas when I'm initially wrong in red, then I tend to change my mind more often. So it's adaptive use of this new evidence, right? So I'm more likely to correct an initial decision that I've made, initially incorrect decision I've made. So these data are, are signatures of the fact people are actually using the new information, but they don't really tell us how does this initial decision and confidence estimate modulate how the post-decision sample is getting integrated into people's confidence estimate. So to look at this, so this is, I guess, another way of in a cartoon showing what I just said. How does this initial decision and confidence estimate modulate how we process this new sample of evidence? And so, one way of looking at that would be to simply take subject's confidence level here and ask how it affects the incorporation of evidence here. And we can do this. But as we know from many other studies, confidence and accuracy, or confidence and performance, are going to be tightly coupled. And so what we'd really like to do is be able to dissociate confidence and performance. And so to do this, we had one other feature of the design that I haven't mentioned yet, which is this manipulation of what's called positive evidence. So this is a psychophysical trick that we can use to create conditions which have higher confidence but unchanged performance. And the trick is basically that rather than having the dots move as in a standard RDK, we now have two streams of dots moving over each other, and we can then independently control the coherence of the two streams. And in a low positive evidence case, the overall coherence level in the two directions is lower, whereas in a high positive evidence case, the overall coherence is kind of ramped up. And so what this creates a situation is that it's equally difficult to decide what's the average direction of motion in these two cases, but it just happens to be the case, as shown by people like Ariel Zilberberg and Brian Odegaard and Hak-Wan Lau and people, that you tend to have higher confidence in this case. Now, it's an interesting question of why that happens, but here we're just going to use this as a black box, like a trick to push around people's confidence independently of their performance. So when we do this, we create conditions that have different confidence but equal task performance, and then we could ask, how does this shift in confidence here affect how we take on board the new evidence here? And importantly, we're not going to play around with the positive evidence here, we're just going to play around with positive evidence pre-choice. Okay, so when we do this and we look at our data as a function of this manipulation, indeed we see people perform similarly in the two cases, low and high positive evidence, but as we hoped for, people feel more confident in the high positive evidence case compared to the low positive evidence case. And this also then leads to, allowing us to then isolate this effect of confidence on subsequent changes of mind. And what we find is that people tend to change their mind less overall when they receive high positive evidence compared to low positive evidence, right? So that suggests that this boost of confidence that we're inducing leads to people being less willing, I guess, to take on board the potentially corrective information. And this is correlated over subjects, so the manipulation effects on confidence, so how much your confidence tends to be boosted by high minus low positive evidence, is negatively correlated with the manipulation effect on changes of mind. So if you have even higher confidence as a function of the positive evidence manipulation, you're going to be even less likely to go on to change your mind. So that provides us with a hint that confidence might be playing this kind of modulatory role on post-decision evidence processing. But to get a more direct readout of how confidence is modulating this post-decisional processing. We we repeated the same experiment in the MEG scanner, and we used sensor level decoding techniques to generate a time course of classifier predictions within the trial that would predict whether the subject would go on to say that the motion is going to the right or to the left. So we can do this in the pre-decision phase, and also then I'll show you analyses of where we train our classifier in the pre-decision phase and then derive predictions for the evolution of that classifier, whether it's predicting right or left motion in the post-decision phase. And so one way we can kind of summarize these classifier predictions is, rather than just looking at the raw predictions over time, we can summarize them with by applying a regression within a trial. So we take the whole time series of classifier predictions within a bin of a few hundred milliseconds, and then we can fit an intercept and slope to this. So you can think of this as like a neural analog of evidence accumulation. So this is grand average data for those classifier predictions as a function of what the veridical motion direction was presented to the subject. This is the pre-decision phase. So this is really just a sanity check. When we present the subjects with rightward moving dots, the classifier tends to predict more and more strongly that the subject will go on to say the dots are going to the right. When we show the subject leftward moving dots, the classifier predicts more and more strongly that the subject will go on to say the dots are moving to the left. And as I said, we can extract out these summary statistics, slope and intercepts, and ask how they predict behavioral measures of decision making in this pre-decision phase. This is more of a sanity check that we're extracting something out from the MEG data that makes sense. And indeed, the stronger the slope here, the faster your choice, the more accurate and the more confident you are in that initial decision. This is just a visualization of the sensors that are contributing most of this classifier, this pre-decision classifier performance at the peak of decodability. And this makes sense, we think, from work from Redmond O'Connell's group showing that this parietal positivity is tracking an abstract evidence accumulation signature in these kind of tasks. Okay, so that's really the sanity check, saying that our classifier metrics in the pre-decision phase seem to make sense in terms of predicting people's choices. But what we're really interested in knowing is, well, what happens in the post-decision phase? So what happens to these neural markers of evidence for rightward or leftward motion in this post-decision phase? And in particular, what happens to these markers as a function of confidence, right, in your initial choice? So we can simply ask, how are these, when we take, say, a classifier prediction that we derive, say, at plus 200 milliseconds in the pre-decision phase, and ask, how is that reactivated at the same time point in the post-decision phase? And so I've now changed the plot in this here, rather than showing you data that's organized according to direction of motion. Now you can just think of this as representation of the correct or veridical motion direction. So if the classifier is going positive, this means that it's responding to the motion direction we actually presented to the subject on the screen. And this is the post-decision period now. So when we look at it in this way, we can sort our trials according to whether this post-decisional information is confirming or disconfirming the subject's initial choice, right? And when subjects initially have low confidence in their decision, then you tend to get a positive slope. So these again, grand averages. I'll show you the stats in a couple of slides. But in general, when you have low confidence, you tend to incorporate or integrate the veridical information presented on the screen, regardless of whether it's confirming or disconfirming your initial choice. But what was pretty striking to us was that when you have high confidence, this now starts to diverge. So when you're highly confident in your initial decision and you get new evidence that confirms that choice, your brain says, fine, let's integrate, right? So that's the top line here. Whereas when you get evidence that disconfirms that initial choice, there's not much going on, right? And this leads to this confidence-weighted confirmation bias. So that's kind of one of the main conclusions of this paper, is that after the confidence seems to weight how much this confirmation bias is applied in this post-decision phase. So after high confidence decisions, the MEG activity is relatively insensitive to disconfirmatory evidence. And we also, I'm not going to talk about it here, but we also show convergent evidence for that idea using behavioral analysis, so using drift diffusion modeling of response times.
Steve?
Yeah.
So it seems when you have a high confidence and you get this confirmed that there's sudden surge, I don't know what the timeline here is, around 200 milliseconds or so, which almost meets kind of the confirmation bias. Is this something which is meaningful, or is it just kind of a bloop? No,
I think that's noise, because we've seen this now in the second data set from EEG. So I think this is basically just an indication that there's not much going on. The disconfirmatory, and in fact you can see that. So this is a grand average, but we can look at the beta of this regression slope for every subject. So this is what I'm going to plot on this slide here, right? So this is now the slope as a function of confidence, so low versus high, and whether the evidence is confirmatory or disconfirmatory. So what you see is that this asymmetry, so there is also a confirmation bias under low confidence on average, but this asymmetry gets bigger, so there's an interaction under high confidence. So basically that wavy line averages out to become almost zero in the group. Yeah. So this increase in slope asymmetry is kind of this marker of this confidence-weighted confirmation bias in the MEG data. Okay, so a couple more results I just want to show you from this data set. So first of all, I just talked about here, all the results I've shown you are along the major diagonal of this temporal generalization matrix. So here we're asking for a given time point in the pre-decision phase, how is that same time point? You know, we train our classifier on, say, plus 200 milliseconds in the pre-decision phase, and we ask at plus 200 milliseconds in the post-decision phase, what is the prediction from those sensor weights trained at that pre-decision time point? But we don't necessarily need to be restricted to this major diagonal. We can look for a particular training time in the pre-decision phase, how is that neural pattern reactivated across all possible times in the post-decision phase? So that gives us some insight into the stability and change of these neural patterns that track evidence for right and leftward motion. And so when we do that, so this is what I'm going to show you here, and we can then ask, how does confidence modulate that temporal generalization pattern? And so this is a slightly, is a bit tricky to get your head around this, but what I'm showing you here is the effect of confidence, high minus low, on that temporal generalization pattern. No. I'm getting a little bit of interference. Okay, we're all good. So on the effect of confidence on that temporal generalization pattern, and this is looking at the decodability of this initial decision. So, you know, how well can you decode evidence in favor of the confirmatory response? And what we see is this cluster, significant cluster on the off diagonal, where for several early time points in the pre-decision phase, this is on the y-axis here, you get early reinstatement in the post-decision phase. So one tentative interpretation of this is this reflects kind of an early bias, if you like, towards evidence in favor of that initial decision. So this is a kind of almost a rapid reactivation of a processing stage that takes a little while longer pre-decisionally, but post-decisionally it's almost like the brain is in a prime state to process evidence that's in favor of that initial decision. Okay, so just one final result here. So, so far I've told you about results from the MEG data where we're decoding the left versus rightward decision. Now we also had subjects respond on every trial whether they were high or low confidence about that decision. So we can also apply a similar binary decoding analysis to decode whether the subjects are high or low confident. at each time point in the pre-decision period. And again, we can do this. So the cross-validated accuracy is similar for both decoding of left versus right motion as it is for decoding of high versus low confidence. But what we can then do is take the peak decodability of these two different decoders, one for left versus right evidence and one for high versus low confidence, and ask how does that predict whether subjects behaviorally go on to change their mind later in the trial. And we found this pretty interesting because what we found is that there was, they don't code for the same thing. So the strength of evidence, so the absolute value of this left versus right decoder, doesn't really do much for predicting whether you go on to change your mind. But the strength of the confidence classifier has a strong effect on subsequent changes in mind. So it's negative because when you predict higher confidence, you should be less likely to change your mind later on. And what we think is going on here is that just like we can drive around people's confidence behaviorally independent of performance using the positive evidence manipulation, there are potentially separable neural patterns tracking the first order evidence for left versus right motion and this second order attribute of confidence. And so to kind of get some support for that, statistically we can throw this into a mediation analysis. So we have the positive evidence manipulation, high versus low, which we know behaviorally leads to fewer changes of mind. And we then enter either the strength of evidence for left versus right motion or the confidence classifier prediction on a trial by trial basis into this mediation analysis. And what we find is that the confidence classifier mediates the impacts of the positive evidence manipulation on whether people change their mind. Okay, so just to sum up the data from this study. So we can decode decisions and confidence levels from sensor level MEG activity. High confidence is associated with a confirmation bias, both in behavior. So there's modulation of the drift rate. I didn't show you those data, but it's in the paper. And these MEG signatures of post-decisional processing. We can find confidence-related signals during this pre-decision period that are partially independent of signals predicting the choice, left versus right. And these confidence-related signals go on to predict whether subjects will change their mind or not. And so this tentatively suggests, although we're dealing with whole brain sensor level activity here, it suggests that potentially higher order or parallel confidence representations might be modulating subsequent information processing. Okay, so I'm going to speed up a little bit now for this middle section because I want to hopefully have 5 minutes to talk about the last part as well. So here I'm just going to expand out and talk a bit about how we can also study similar roles of confidence, not only in the processing of passive information, but also how we actively seek information. And in this study, I'll also tell you about how, because this was study was done online in a large data set, we also had the opportunity to ask, does that relate to any real world features of people's attitudes, in this case about political issues. So intuitively, when we make a decision, we have some confidence estimate about that. That might affect how we passively process information, but also it might affect how we actively sample information. Do we go and read the news? Do we look up things on social media and so on? So to study this in the context of these perceptual decision-making paradigms, we could modify our paradigm. So now, rather than just passively presenting people on every trial with new evidence after their decision, we gave them an active choice about whether they want to see that new information again or not. And the reason that this was a meaningful decision was that it cost them a little bit of points to see that new information again. So on some blocks, this was a small cost, -5 points. Other blocks, a high cost, -20 points. And if you chose to see the dots again, then you got a new sample of evidence. And if you chose not to see them, then you just had to wait the same amount of time. So choosing not to see new information didn't mean you got out of the task faster. It just meant you didn't get to see anything, but you didn't pay the cost either. And then at the end of the trial, subjects had a final decision to make, and this was incentivized. So if they got it right, they got 100 points, wrong, they got 0. And I should mention that, as you can probably see already, this is not random.motion. This is being done over the web, and we're using a task involving choosing which box contains a higher number of flickering dots. So this is kind of like a web analog of random.motion. But it allows us to also then control the difficulty in a similar way, and we can apply staircase calibration to titrate the evidence strength for each subject in the sample. So this was work conducted by Leon Schultz when he was a master's student in the lab. He's now a PhD student with Peter Dayan, also with Max Rollwager. So just to show you that people make sensible decisions here, so they tend to seek more information on the y-axis when they're wrong initially than when they're right, so that makes sense. They also tend to seek more information when it costs less, also makes sense. And perhaps most importantly, for our hypotheses here, they seek more information when they're less confident in that initial choice. So there's a nice graded effect of confidence on information seeking here. As I mentioned, we also have the opportunity to collect some questionnaire data on all the subjects in this study. And in particular, building on a previous study we'd run, we were interested in this trait of dogmatism. So how certain you are that you're right and everyone else is wrong, effectively. And we embedded this dogmatism questionnaire in a series of other questionnaires on political orientation. And we then applied a factor analysis to the whole set of the whole questionnaire battery and extracted 3 key factors. So the first one is simply tracking whether you're more left-leaning or right-leaning. This was all a US sample, so some of the questions were about whether you voted for Democrats or Republicans and so on. But the key factor we're interested in here is this dogmatism factor, which unsurprisingly is mainly driven by the dogmatism questionnaire, but also includes elements of these kind of authoritarian traits. And so just to give you a sense of what this dogmatism factor is picking up, this is the highest loading item. I'm so sure I'm right about the important things in life. There is no evidence that could convince me otherwise. Right? So this is really tapping into this kind of belief rigidity. And so we can then simply ask, how do features of our task predict fluctuations in, predict individual differences in dogmatism? So that's the standardized beta coefficients on the y-axis here. And we had an internal replication, so we had 2 separate samples of almost 370 people. And what we see is that consistently across both samples, the extent to which you seek information is a very simple metric. So just how much information do you seek negatively predicts dogmatism. So if you're more dogmatic, you're less likely to seek new information in this perceptual task, all else being equal. And interestingly, that wasn't related to just your level of confidence overall, your mean confidence, or how good you were at the task overall. So it was really seemed to be quite specific to this, this kind of secondary information seeking choice. And because seeking information in this task is helpful, what this means is that people who are more dogmatic also tend to be overall less accurate at the final decision, not at the initial decision. Just as good as everyone else at the initial decision, but when you then give them an active choice about whether to seek information, they say, no, I'm good, and they don't seek it, and then they become worse overall. So this is showing that the negative relationship between dogmatism and final decision performance is mediated by the extent to which dogmatism reduces your tendency to seek information. So that's a relatively coarse level analysis. It's simple summary statistic of how much you seek information. We want to go a bit beyond that and look at trial by trial, how is dogmatism affecting the relationship between the different variables that predict information seeking in our task. So we set up this simple logistic regression model where the probability you seek information on every trial is linked to some baseline tendency to seek information, and then these 2 factors that we saw predict information seeking. So how confident you are in your initial choice, and what's the cost of seeking that new information. We can then embed these beta coefficients in a hierarchical regression model where we're asking, how does the strength of these predictors itself depend on individual differences in dogmatism. And what we find is that for this beta 0 parameter, we get the expected effect from our simple regression. So we get, this becomes more negative when people are more dogmatic. So that's just replicating the simple regression. You know, more dogmatic people are less likely to seek information overall. But what's interesting is this beta 1 parameter, this confidence related parameter here. So this is actually positive in relation to dogmatism. And what this means, because overall in the group as a whole, it's actually negative, you seek more information when you're less confident. What this positive effect means is effectively that in dogmatic people, it's less negative. So it's weaker when there's a weaker link between confidence and information seeking in more dogmatic people. And interestingly, there's no effect of cost. So that's pretty much bang on the 0 point. So we can visualize this effect of confidence. It's sometimes a bit hard to get your head around, but basically this is what the model predicts, and this is the actual data. So if you just do a median split on dogmatism, then when people are very confident, there's not much difference in the groups. So when they're very confident, both less and more dogmatic people will say, I'm good, I don't need more information. The difference emerges when you're less confident. So when you're less confident and not very dogmatic, that will prompt you to seek out the new information. Whereas even if you're dogmatic and less confident, you might be still reluctant to seek out the information. So this just kind of flattens out the slope between confidence and information seeking in the more dogmatic people. Okay, so in the last 5 minutes or so, then what I want to do is kind of hopefully strike a slightly more optimistic note on which to end, so we can all go home happy or stay at home happy. So far I've kind of made this argument that, you know, metacognition is a good thing because it, you know, potentially promotes open-mindedness to new information. But that latter study suggests that, you know, when that link between confidence and information seeking fails, or then that might shut us down to being open to new information and to change our minds. So that naturally is the question, well, can we then, you know, harness or boost metacognition to potentially improve decision-making and increase open-mindedness? So the idea here is that, you know, as I just said, good metacognition should make us aware of when we've made an error. That should promote better decision-making and potentially ameliorate a confirmation bias. And we already see evidence for this kind of effect in the MEG data that I mentioned earlier. So if you remember in our paradigm here, we're not setting out to trick subjects, right? So when they get disconfirmatory evidence, those are trials where they're rigidly wrong about their choice. So this means that what really matters is how people respond to disconfirmatory evidence. You know, how do they respond to evidence that is telling them that they were initially wrong? So what we know from our MEG and behavioral data is that when people are highly confident and they get disconfirmatory evidence, it's not processed very much, right? They seem to be selectively ignoring that. And so these would be cases where they're also metacognitively inaccurate. They're highly confident after an incorrect decision. Whereas over here, these are also cases where they get told that they were wrong, that they get disconfirmatory evidence. But here they had low confidence on these particular trials. So these would be metacognitively more accurate decisions. So they're sitting in this box here rather than this box down here. So the simple argument is, what we'd really like to do is move more trials from this bubble over to this bubble, either at the level of within an individual or across individuals. We want to move more people to have this kind of response than this kind of response if we want them to be open to corrective information. I'll just very briefly highlight this. It's a bioRxiv paper, so if you're interested, you can go online and read more. But basically, Max also ran some simulations of this kind of model where what we see is that in a model where we allow people's sampling of new information to depend on their confidence, what we find is that the confirmation bias agent is impaired relative to an unbiased agent, but this impairment is actually reduced when we allow the confirmation bias to itself depend on confidence, and it's even more reduced when we have better and better metacognitive efficiency of our simulated agents. So I won't go through all the details of this for the sake of time, but generally this simulation supports this idea that better metacognitive efficiency promotes more open-mindedness to new information, makes the agent more accurate in the long run. Okay, and then yes, finally, just another piece of evidence for the idea here. This is a different study, again, in large online samples, where we were able to measure both metacognitive efficiency in one task, but also post-decision evidence sensitivity in a second task. And what we found is in two separate samples that metacognitive sensitivity measured here predicts the degree to which you'll take on board the new evidence in the second task. So again, it suggests this kind of general link between having good metacognition and being open to corrective evidence. Okay, so the potentially nice thing about this is that we know from other work that metacognition might be malleable, it could be trainable. So this is work that was done in collaboration with Hak Van Lau's group, led by Jason Carpenter, where we developed a metacognitive feedback protocol where over a period of 2 weeks, people performed around 20 minutes training a day over the web, and they got feedback on how close their confidence matched their accuracy in a simple perceptual task. And what we found is that in the experimental group, so this is the calibration score or a metric of metacognitive sensitivity on the y-axis here, what we found is that in this group that got the metacognitive feedback, their calibration improved. But the cool thing for us was that not only did it improve, it also transferred to a completely untrained task. This is the blue symbols here. So this is a memory task. They've never received metacognition training on it. But when we train up their metacognition of perceptual task, it also boosts their metacognition in an untrained memory task. So that potentially promising for more domain general or generalized effects here. And we're now working with a game design company in London to try and bring some of these insights into a more user-friendly framework where we can both measure and potentially train up metacognition in a wide variety of settings. Okay, so just a final data point I want to show you. So this is work, a heroic study conducted by Max Rollwager and an undergraduate intern, Pippa Watson, in the group, where effectively we just combine these pieces together. So we measure people's post-decision evidence sensitivity both before and after metacognitive training using exactly the same task I described in the first part of the talk. We also had EEG measurements pre and post, so we could look at the sensitivity of these new neural markers of post-decision processing. And we had people in between go home and do this web-based metacognition training in their own time. So the first thing to show is that we see in the group as a whole that metacognitive efficiency is improved after training compared to before training. We did have two different groups here. We had an experimental group and a control group. What I'm not showing you here is that the control group also improved in their metacognitive efficiency. So that's a different discussion. We think there are reasons for that. But what I'm going to show you here is just everyone pulled together. So there's just a general effect of metacognitive training on metacognitive efficiency. But importantly, what we also show is that people are more likely to take on board the post-decision evidence after training compared to before training. And well, that hasn't come out very well, sorry. So there should be another little graph up here which tells us how much they're changing their minds about correct decisions and incorrect decisions. So you just have to take my word for it that there's no effect on the correct decisions. But what people are doing better after training is they're more likely to change their minds about initially incorrect decisions. So it seems to be a selective boost in their processing of evidence that contradicts their choice. And importantly, there's no effects of training on the initial decision sensitivity. Okay, this is really just the kind of neural correlate potentially of that, which is again these decoder traces of confirmatory and disconfirmatory evidence processing before and after training. And at the group level, we get a significant boost in both of these slopes after the training. So they seem to become more sensitive to the post-decision evidence, both behaviorally and neurally. But I think the most important result here that we have in this study is this one. So both at the level of simple correlations, but also the level of mediation. So the more the training boosts your metacognitive efficiency, the more it's also likely to make you open to this post-decision evidence. So this is all within the context of a perceptual task, obviously, and we'd love to know, what would happen to a range of real-world tasks where we're asking people to update their beliefs. So that's something we're still working on. But in general, I think this is a nice proof of concept that by boosting metacognition, using this kind of intervention, we might be able to make people more open-minded about evidence that might be correcting or challenging their views. Okay, so just to wrap up, so I've shown how these metacognitive representations of confidence modulate how we process new evidence and seek new information. Both decisions and confidence levels can be decoded from sense level MEG activity, and in particular, the confidence-related signals predict whether or not people go on to change their minds. This suggests a role for higher order confidence representations in modulating ongoing information processing. Higher metacognitive sensitivity in that kind of framework should then normatively promote integration of new evidence when it is most needed after you've made an error. And that means, or it highlights the potential for metacognitive training as a promising avenue for promoting and maintaining open-mindedness to new information. So I'll stop there. I just want to thank my lab, and in particular for this line of work, Max Rollwager, who recently graduated, finished his PhD in September, was instrumental to all of these studies. And thanks very much for the invite and for everyone being here.
Thanks a lot, Steve. A fantastic and interesting talk. Yeah, so we're open we have some time for some questions. People are welcome to shout out. Yeah, Adam?
Thanks for the great talk. Just a question on this last work about metacognitive sensitivity. Do you really need to improve their sensitivity, or is it enough just to lower their confidence bias? If they have a lower bias, then they'll also be more willing to integrate other information. So how do you differentiate whether it's really sensitivity or, as you showed, the baseline bias?
Yeah, so I haven't got this data to show here, but we actually typically see in this kind of protocol that people increase their bias while also improving their sensitivity. So we think that might reflect a kind of base rate effect, because in general, people are performing above chance on these tasks, right? So if they do tend to assign correct trials to high confidence and incorrect trials to low confidence, you might also predict a boost in bias. So if anything, we see the opposite to what you suggest there. So people seem to increase their confidence. Now, I guess it's still an open question then, what would happen if we could devise a different protocol that lowered your confidence overall? Yeah, I don't know. It's a good question. I think one line of evidence that sensitivity might be important rather than bias is that in those kind of individual difference studies that I talked about earlier, the main predictor of things like taking on board new evidence or seeking information is the sensitivity, not the bias. So just your overall level of confidence doesn't seem to predict very well your post-decision processing. So yeah, interesting to think about like what would be the best intervention. And in these training studies, we're kind of stumbling around in the dark a bit because we don't really know how best to intervene and train people up to improve their metacognition here.
So I have a question. So, it would be fantastic if everyone had very, very good metacognitive efficiency, and I can see how that would be good. but it seems that you're always pushing in the direction of kind of boosting people's metacognition and confidence. And I think some of these biases are there for a reason. And I'm wondering, you see this both in some clinical syndromes, but also in non-clinical populations. Second guessing in the abundance of information we have now is a terrible thing. It can really damage your performance.
Yeah. Yeah, no, I think that's a great point. And I think that there are certain reasons why we might want to be cautious about thinking this is unalloyed good, that we should all be improving metacognition. So, I mean, in other work that I haven't talked about today, we've been also looking at the link between these metrics, these task-based metrics of metacognition and variation in mental health symptomology. And along the lines you suggest, people with higher anxiety also tend to be the ones who have better metacognitive sensitivity, which seems to be related to the fact they're more aware of their errors, right? So yeah, maybe you don't want to overdo it, if you like, and get too much insight into your mistakes if that's going to have negative consequences for things like anxiety. But I think on balance, and also I should say that, there's other people who work in the intersection between metacognition and mental health have made similar points about, for instance, in dementia, is it a good idea to boost people's awareness of their memory failure? I mean, there's a lot of people think it is, but maybe that could cause unwanted anxiety as well. So yeah, I think it's interesting to consider. I think it's like all of these things, the kind of effect sizes we're working with in the lab are small and they're not very long lasting as far as we can tell. But if we were to get to a point where we had some kind of intervention that we wanted to roll out, then it would become like a drug where we want to look at side effects and all that kind of stuff. So I think at this point, there's more promise for boosting for a variety of reasons than not. But I completely agree. We'd want to avoid unwanted side effects.
Okay, anyone else? Sorry, I heard someone asking, but I think I cut someone off.
Yes, I have a question. Thank you for a great talk. I was wondering if you spoke a lot about the accurate and the wrong decisions, but I wonder if you saw effects on reaction times. So when you boost people's metacognition?
Yep. So in that very last study, we don't see effects on response times at the group. So just as a kind of, just as a, what is your average RT for that secondary decision? We don't see effects on response time, just like we don't see effects of training on D prime on first order performance. But I think it's, there's an interesting question there about like, how does the training alter these richer evidence accumulation parameters on that secondary stage? So if you start dividing up the conditions according to confirmatory and disconfirmatory evidence according to confidence, then you start to see effects on the drift rate, just like we see effects on the slope of the MEG, on the EEG evidence accumulation as well. So I guess the short answer to the question is we don't see group level RT effects, but at the within subject level, we see RT effects that you would imagine would go along with a more veridical integration of this post-decisional information.
Okay, Adam, you have another question? Go ahead.
Yeah, so I wanted to ask regarding in your information-seeking task, it seemed like there was an effect of age, at least in one of the groups. Was this a spurious effect, or could you say something about that?
Yeah, that was, maybe I can go back. So, yeah, this one you mean? This one?
Yeah.
Yeah. Well, yeah, we don't really know because it didn't appear in the first sample. So, sorry, I should have said, I probably didn't say this, that the two regression coefficients side by side are the two samples here. So we see this effect in the second sample, but not the first sample, and the only metric that replicates across the two samples is this information seeking one. And this is partly why in our lab, when we've been doing these big online studies, we found it extremely useful, time and resources permitting, to just do a straight replication, because it's, you know, so easy in these Amazon Mechanical Turk recruitments to do that. And we do sometimes find, you know, you get effects in one sample that don't replicate in the other. And so we're reassured by the fact the information search one does. Yeah, I don't know, when we saw this, we also then thought, okay, let's make sure it's not related in any way to this information search phenomenon. It doesn't seem to be related. So when we actually look for direct links between age and information seeking, we don't see them. So yeah, I don't know. This, I mean, what this basically means is that when you're older, you become more dogmatic, but which I guess might make sense, right? But like it didn't replicate across the two samples.
So if no one else has a question, I have a question, which, you know, is our mutual area. Michal, go ahead.
I'm curious if we can talk more about domain generality, because, and maybe I missed it, but I think most of the decisions here at the bottom are perceptual decisions. And how much do we know whether these, let's say, parietal systems, are they really involved in evidence accumulation, broadly speaking, or is it specific to perceptual decisions? Suppose somebody goes to make a decision about getting a vaccine or not. Suppose, you know, the decisions are completely non-perceptual.
Sure.
Do we have evidence that this is relevant?
So I guess there's there's lots of interesting things about your question there. So on one level, I think there's good evidence from Redmond O'Connell's group that these parietal evidence accumulation signals at least generalize to multiple perceptual tasks, not just visual, so auditory as well. So they see at the level of EEG, they get this central parietal positivity, which seems to track the strength of evidence accumulation in a more abstract and stimulus and response independent manner. So that's quite promising for the notion of a more abstract evidence accumulation signal. At the level of metacognition, we certainly think that from a variety of sources of evidence that, for instance, the kind of training effect I showed you at the end, that when we train people's confidence upon a perceptual task, they also get better at metacognition on a memory task. So that would be evidence for transfer to different types of tasks and even tasks that don't involve perceptual integration. But I think the kind of million-dollar question here is, how does it generalize to things we care about, like in terms of real-world decisions about vaccines, about climate change, that kind of thing. So I hesitate at the moment to show this slide, but I'm going to show it anyways. I think I've got it at the end. So we did, in this training study, include, okay, here we go. We did include some questions about this. So we thought, you know, maybe this is a bit of a moonshot, but maybe it'd be interesting if it did work out that way. And I think we've got some tentative evidence that it does. So what we did here was ask people, unfortunately, we didn't do it twice. We didn't do it before and after training. We just did it after training. But we asked them to rate how severe they thought climate change was. This is taking questions from a study from Helen Fischer, who's a climate scientist in Germany. She's interested in the role of metacognition in processing climate change related information. And what we did was we looked at, after we give people factual information about climate change, how much do they then update their rating of how severe it is? And we found that the people who had more of a training effect on metacognitive efficiency were also more likely to update their ratings about climate change. Now, this correlation doesn't look very impressive. So we also then looked at another data set that was freely available online, where there's a very similar type of association you can reanalyze there. So this is a whole series of general knowledge questions. And again, they ask you to rate, it's on a continuous scale, like what year was Shakespeare born? So you give the date, and then you get some factual information, and then you have to give the answer again. So they can measure on a continuous level how much do you update towards the factual information. And they also had confidence ratings in those initial decisions. So we could reanalyze their data and compute metacognitive efficiency about those questions. And what we see here is that metacognitive efficiency about general knowledge is correlated with how much you update your beliefs about these general knowledge questions. So this isn't telling us anything about domain generality, but it's telling us something that maybe similar processes are involved. This is tentatively telling us something about domain generality. I think you're on mute, Roy.
Yeah, I'm on mute because the kids are on a rampage behind me. So do we have any other questions? So Steve, we only have maybe 5 minutes. I was wondering if you maybe want to say 1 or 2 words about how you think these kind of metacognitive representations impact what we experience or our consciousness. What's this interplay between this? Kind of very brief as a teaser for the next time I invite you.
Just in 5 minutes, right? Just the easy question at the end.
Yeah.
Yeah. So, I mean, this is something that I always struggle with a little bit. So, I mean, we have kind of 2 lines of work in the lab at the moment. One is on metacognition and the kind of things I've talked to you about today. And the other, which we've increasingly been getting started, is on conscious awareness, often in perceptual tasks more specifically. So, you know, using thinking on a computational and cognitive level, what are the processes involved in judging our experience? And aside from those both being metacognitive judgments, I'm not so sure how common, you know, how much commonality there is. So I think one, to the extent to which metacognitive measures of, say, decision-making tasks are telling us something about the ability to reflect on a previous decision episode, if you like, then that ability to reflect might be related to the notion of meta-awareness, so kind of becoming aware of perceptual experience. But I think it's really hard to know where to start on testing those links. So I think conceptually they seem to be related. And I like the idea that, you know, becoming more open-minded and becoming aware of our failures is somehow related to becoming more conscious of more basic features of our experience. But, you know, like becoming lucid in a dream, it could be something like that. But I don't know. Like I think it'd be great to know, and maybe metacognitive training gives us some insight into this. You know, if we have tools to push around metacognition, then can we then start studying its consequences for, say, perceptual experience, conscious experience? And I think at the moment we just don't know enough about how these kind of training procedures work. But if we can nail that down, then I think it'd be really nice to think about how that might impact on more basic features of conscious experience. I mean, one link that I like is the in the literature on lucid dreaming. When you're normally dreaming, you're not self-aware in a metacognitive sense, typically, of your dream. But some people can dream lucidly and they can report being aware of their dream. And that sounds really fun. It's only ever happened to me once. And it was great. You could like fly around the room and you'd be aware of flying around the room. But what's fascinating in that literature is there's been some, you know, amazing studies done using brain imaging to show that when you become more lucid in dreaming, you activate similar brain networks to those involved in metacognitive sensitivity. So, and that's data, you know, I didn't talk about today, but that's a whole other line of work we're interested in. Like, what are the neural correlates of having better metacognition? And so, you know, there's a kind of really cool, but potentially, you know, quite speculative reverse inference you could do there, that like perhaps boosting metacognition potentiates this feature of self-awareness and that boosting metacognition in daily life might feel like becoming lucid in a dream in a very like coarse way. So yeah, that I think is exciting to think about, but obviously quite speculative.
That's exactly what I wanted to hear.
Good.
Fantastic, Steve. So let's please all thank our speaker once again for a great talk. It's a lot of fun to have you.
Yeah, thanks everybody for the great questions, and yeah, really fun to be here. So yeah.
Great, thanks a lot. So everyone keep safe, and yeah, and keep working from afar.
Yeah.
Soon. This will all be over soon.
Absolutely. Absolutely.
Bye. See you all. Thanks a lot.
Thanks everyone.